So what is a capacitor? Well, a capacitor is an electrical component that can store electric charge. Well, storing electric charge is pretty easy. It means creating an imbalance in charge in an object. It means that instead of being neutral, we've either added electrons or removed electrons. Conductors are pretty good for doing this. You could do it to an insulator. We know that we can charge an insulator with using friction and create an imbalance in charge. But with a conductor, because the charge can flow freely throughout the conductor, it's pretty easy to get electrons off or on. Well, the normal design of a capacitor, therefore, is two conducting plates, metal plates, nearby and separated by an insulator. And that's called a parallel plate capacitor. Well, the reason for having them pretty nearby will become clear in a minute. But one way to charge these two plates up would be to connect them to a power supply. So we can connect the left-hand side plate to, say, for example, the positive terminal of a power supply, and we might connect the right-hand side plate to the negative terminal of the power supply. And we can sort of imagine what's going to happen. Before we connect, both plates are neutral. They've got as many protons as electrons. But once we connect that power supply, well, electrons on the left-hand side plate are going to get attracted towards the positive terminal. And so there's going to be a sort of flow of electrons away from that plate. And similarly, the negative terminal is going to push electrons onto the other plate. So we're going to end up with a situation where we end up with the left-hand side plate has got now a few electrons missing, and therefore it becomes overall positive charge. And the right-hand side plate's got too many electrons now, so it's not neutral anymore, and it's got an overall negative charge. Well, we say that the left-hand side plate has now gained, therefore, a positive charge. And the right-hand side plate has gained a negative charge. And they're going to be equal in magnitude, because as many electrons that have come off the left-hand side plate have flowed onto the right-hand side plate. And so in this situation, we would say this capacitor is charged to a charge of Q coulombs, not 2Q, because it's only 1Q that's actually flowed from one plate to another. Well, now we can see why a parallel plate situation is pretty good and pretty efficient for storing charge. You can imagine that if I put the plates even closer, well, there's a kind of attraction mutually between the positive charge on one plate and the negative on the other plate. And if I put them even closer, well, that attraction is going to be even stronger, and it's going to help hold that charge in place. So this one would be an even better capacitor just because the plates are closer together. Also, we could improve the situation by making the plates a much bigger area. The more area we have, then the more easy to remove charge. This process is obviously going to have a point where it stops working. What I mean by that is that if when we connect our power supply, well, at first it's pretty easy to remove electrons, but as we end up with less and less electrons on this plate, well, it's trying to attract the electrons back, and there's going to come a point where the electrons are attracted back as strongly as they're attracted to the positive terminal of the power supply. And that's going to be the same whatever situation we have. Let's look at what an actual capacitor looks like. Well, if you've ever seen a capacitor or used one, you've probably seen that it looks like this. And so one question that arises is, well, you know, how is that a pair of parallel plates? And it's good to know the answer to that. Well, the design is typically a kind of Swiss roll design, where you've got the two plates are pieces of metal foil, typically, and in between is an insulator. In our case, we had air between the two plates, which is a great insulator, but obviously if we're going to roll them up, that would be really difficult. And actually the efficiency can be improved by using different materials. An insulator, a thin piece of paper, for example, means that the plates are really close together, and doing this kind of Swiss roll formation means that we get a big surface area on the two plates. So the plates are close together, and not only that, there's a large surface area. So we end up with a really nice, good capacitor, a good possibility of storing loads of charge. The circuit symbol for a capacitor, you'll know, is these two parallel plates, which makes a lot of sense. So from now on, we'll draw them in that way. So we've seen that if we have a parallel plate capacitor with, say for example, a big surface area of plates or plates very close together, we're going to have a bigger ability to store charge. And well, the ability to store charge is called the capacitance of a capacitor. And it's actually got a very formal definition, which is that the capacitance C is the charge stored per volt between the plates. And it turns out that this is a constant. So if we plot a graph of this situation, well, the more volts we put between the two plates, the bigger the power supply we use to charge a capacitor, in other words, well, the more charge we store, and that they're directly proportional. I could rewrite the equation, for example, as Q equals CV, which means that the charge stored is directly proportional to the potential difference between the plates. And that's clearly going to be there for a straight line. And hopefully you can see that the gradient of that line is going to be the capacitance. Yes, because if I compare with y equals mx plus c, there's no intercept, and therefore if I plot q on the y-axis and v on the x-axis, then I'm going to get a gradient is going to be q over v, which is q over v, which is going to be c. Okay, so that is pretty useful information. What is capacitance measured in? Well, we can see from the equation that this capacitance here is measured in coulombs, because charge is measured in coulombs, per unit volt, or per volt. And so that is therefore the unit. The unit is coulombs per volt, or CV to the -1. But that's actually renamed, and it's renamed as the farad, or the farad F. And the farad, therefore, is how we describe capacitance of a capacitor. Let's have a look at that capacitor again, because we can see there that it's got a bit of information marked on. First of all, there is a value 47 mu F. Well, that is the capacitance. So the capacitance of this particular capacitor is printed on, and the capacitance is 47 microfarads. Well, we know that that's 47 times 10 to the -6 farads, or might be nice to write it in standard form. That would be 4.7 times 10 to the -5 farads. So that information is given because there's a vast variation in capacitance of a capacitor. One thing we do notice is that that value is pretty small, and that's a general feature of capacitors. 1 farad is a huge capacitance, and so typically capacitors are going to have capacitances down in the microfarads, even picofarads. There's another figure on there which, even though it's upside down, hopefully you can see is 450 volts. Well, that's the working voltage, and it's the maximum voltage that you can use with this capacitor, and it's pretty important, you know, not to exceed that, because if you do, the capacitor is going to break down. So that's pretty important. Well, let's just see how this equation works then. Well, if we charged it to its maximum working voltage, so if we actually connected this capacitor to a power supply of 450 volts, which is the maximum we're allowed to use with this particular one, then we know that the capacitance is 4.7 times 10 to the -5 farads. So we could figure out the charge stored. Well, the charge that would be stored at that point is just C times V, and we can multiply those together, and we see that it's going to store the amazing quantity of 0.021 coulombs. So, like, we know it's not going to be much because of that small capacitance, but that's pretty significant. That's a lot of electrons, of course, moving from one side to another. And just for comparison, I mean, because we know this is proportional, let's imagine we just charge this thing to 200 volts. Well, we can do the same calculation and use Q equals CV to find out how much charge we'd store in this situation. Well, it's nice and simple to work out because we're just using Q equals CV again. And this time we get a much smaller amount, 0.0094 coulombs to two significant figures. So that's how it works. So that's the basics of capacitors and capacitance. And we've got our first formula that we need to be able to understand and use, and our first new unit, the farad. Next, we're going to look at work done and energy involved in charging capacitors, and then we're going to see how they're useful and start to look at their behaviour in quite a lot more detail.